Hey everybody, it's Professor Stevens. I want to go over some of the notes we did in class today, specifically solving by completing the square. You do need to know how to show the steps of completing the square for the test. Now let's go through the steps here. So we start off with a quadratic equation like this, and we've been asked to solve it by completing the square. So we're going to turn this part of it, the first two terms, we're going to add a constant that will make it into a perfect square trinomial, which can be rewritten as a binomial squared. So the steps here are to move the constant term over to the right, so you can see that -9 there, to make space for where you're going to complete this into a perfect square trinomial. Then, if you have a coefficient other than 1 like we do here, we will divide through to get a coefficient of 1. Now, remember during class I mentioned that the reason, or one of the ways that you can remember that you really do need to divide each and every term by that value is the idea of distributing a when you're multiplying on a quantity, we distribute the multiplication. And the same thing is happening here. This entire side could be seen as being inside parentheses. And when we divide by 9, we use the distributive property. Or you could also think of it as multiplying everything through by 1/9. So then we cancel that, simplify it, and you can see the next step here, which there are notes over here on this side. These notes actually are supposed to go with this step, where we figure out what we're supposed to add the square of. So what we do is we divide the middle term's coefficient, which will include the sign with that. You divide the middle term's coefficient by 2, or you take half of the middle term's coefficient. So here's the middle term's coefficient times half, or divided by 2. And then squared, right? And the square of that is +4/9. So we've added the same quantity to both sides of the equation, keeping everything equal. Now, I had a question during class about why we always have to take half of that middle coefficient. And so when I get this question, I always refer back to the perfect square trinomial pattern. Our goal is to get something that looks like this so that we can take the square root of both sides, use the square root property to solve. So that is our goal, which means we're trying to turn that original couple of terms, we're trying to add something onto it to make it a perfect square trinomial that can be written in the form of a plus b, or a minus b for that matter, quantity squared. Either one depending on the situation, right? Okay, so knowing that, if we think about what happens when you square a binomial, then you can understand what happens to the middle term when you expand to the quantity a plus b multiplied by itself, the entire quantity again, and we do the FOIL, or we're distributing a times a times b, and then b times a, b times b, and the middle term is a double of the product of a times b. That's what happens every time. So if we are in a situation where we want to know what b squared is so we can complete a square, we actually need to take half of that simplified middle term and then square it, right? So it should make sense from that perspective instead of just memorizing it as something that we do. The other thing I wanted to point out is this common mistake of thinking that a binomial squared simplifies to a squared plus b squared like that. That is a very common error, but like you see here, when you're squaring a quantity, you have to make a copy of that quantity and distribute the multiplication. So that's a common mistake. Something that sometimes I think students are getting it mixed up with is the fact that you can distribute an exponent to factors of a product. Well, that's different. If you expand this out, like you see here, and then use the commutative property of multiplication to rearrange your factors, and then simplify a squared, b squared, that actually works, right? So all of these rules that you learn in math, they're not really just rules, they're things that are kind of like shortcuts or tricks, that once you're used to how things work out, you can skip the expansion and the rearranging and all that, and you know that when you have a product squared, you can actually distribute the square to both of the factors. Whereas here, you don't have that. Instead, the trick, the shortcut is to realize that when it gets multiplied out, you have a squared plus b squared, and in the center, twice the product of a and b. So that's the trick for that kind of thing. All right, now let's just drive this home a little bit and compare some different function representations of a quadratic. All right, so we have been in the section of solving quadratic equations, which is really a review from intermediate algebra. And what we're going to be doing soon is extending the concept of a quadratic equation to thinking of it in terms of a function. And when we think of it in terms of a function, we think about graphs a lot more. And I want to show you how I can graph this binomial squared. What was the answer to this other one? Well, I'll stick with the example that an easy example. So let's say I have x plus 3 quantity squared. It looks like this, right? And then what about if I have, move this over a little bit. What if I have x squared plus 9, right? X squared plus 3 squared. What if I made the mistake of thinking they were the same? So that's x squared plus 9. Let's back up a little bit. Okay, so I'm having trouble getting this where I want it. I should have paused. Okay, so here is what it looks like, the purple line, when you have x squared plus 9. All right, let's look at something else. I just moved this. I want to use a different example. Let's use x minus 3 quantity squared. And then let's try distributing that power. If you looked at it as x squared minus 9 minus 3 squared, then you see the difference there. Now notice that a quantity squared like this, a binomial quantity squared, has only one x-intercept, or only one place where y equals 0, or in other words, only one place where the function equals 0. That's what we call a double solution when we're solving equations. It's also known as a 0 with a multiplicity of 2. Whereas the orange function has zeros, two distinct zeros, one at -3 and one at +3. So that's very different, right? Each of these zeros, x equals -3 is a 0 of the function, and x equals +3 is a 0 of the function because it makes the y value be 0. And those have a multiplicity of 1, which means they're going to cross through the x-axis, whereas multiplicities that are even cause a bouncing effect. So we see the multiplicity 2, this double solution of x equals 3 on the blue function, it bounces and it only touches the x-axis in that one spot. Just kind of interesting to think about. And some of this might be over your head, but when we get to functions later, maybe you'll remember some of this and it'll start to help you connect all the concepts into something more meaningful. All right, now we're going to get rid of that. So that was just to show that they're not the same, but I also want to show you the different forms of the quantity x minus 3 squared. So if we FOILed out x minus 3 squared, we could just expand it first and show that. Let's see. Okay, now notice this just turned purple. It is the exact same function, just showing. What if we showed the multiplied form, the non-factored form. So using that perfect square trinomial pattern, I would have the x term squared. The product of the two inner terms is negative 3x, and double that is negative 6x. And then the square of negative 3 is 9. Whoops, I need plus 9. Plus 9. Positive 9. Negative 3 times negative 3 is positive 9. And then it just turned black. See, it's all the same. So that's that for now. I hope that helped illustrate or clear up some things. And if it just posed new questions for you, maybe you could bring those up to me. I'm always interested in how I can improve my lessons. Suggestions are welcome, constructive criticism. And I hope that this was something useful for you. Please let me know if it was. Thanks.